Hello everyone and welcome back to the Cisco Optics Podcast, where we talk about pluggable optics for networks. Lasers have been around for over 6 decades. Since their invention, they have found their way into many applications that have changed our lives. Optical communications is, of course, one of them, and there are many that may surprise you. There's also still plenty of room to take laser performance to new heights, leading to even more new applications. This is episode 41, and we continue our conversation with laser and optics expert Juliet Gopinath, professor at the University of Colorado Boulder. Next up is her research on using orbital angular momentum in super-resolution microscopy and sausages? Juliet Gopinath is the Alfred T. and Betty E. Look Professor of Electrical, Computer, and Energy Engineering and Physics at the University of Colorado Boulder. She received her BS degree in electrical engineering from the University of Minnesota and her MS and PhD degrees at MIT. She was a member of the technical staff at MIT Lincoln Laboratory from 2005 to 2009. Since then, she has led a research group at the University of Colorado Boulder. Her current research interests include ultrafast lasers, nonlinear optics, mid-infrared materials, spectroscopy, orbital angular momentum, and adaptive optical devices. She has published 78 peer-reviewed journal articles and over 97 conference presentations. She is a recipient of an R&D 100 award in 2012 and is an Optica Fellow. She served as an associate editor for the IEEE Photonics Society Journal from 2011 to 2017, the associate director for Qubit in 2019, and is currently an associate editor for Optica. Juliet also teaches a free online course on active optical devices. Just go to coursera.org and search on active optical devices or search on Juliet Gopinath. If you haven't already, please subscribe to this podcast. On Apple Podcast, you would click the follow button at the top now. We're part of the Cisco Podcast Network. Check out our blog at blogs.cisco.com and search on hashtag Cisco Optics Blog. All one word, no hyphen, and no spaces. You'll find podcast notes and links there too. For our YouTube playlist, go to youtube.com and search on Cisco Optics. And for product information, go to cisco.com/go/optics. And now join me as I talk with Juliet Gopinath.
I can talk about our work on orbital angular momentum of light.
Okay.
So this is something that happened basically purely accidentally. We were working on a project to show that we could use our tunable lenses to make a beam quality measurement. Beam quality basically means how well behaved is your beam. If I send it through a lens and I calculate what the focal spot is that what I'll achieve? And so the goal was that we could we would be able to use a tunable lens and make a nicer beam quality measurement rather than the conventional way of doing it. And so we wanted to be able to demonstrate with some ill-behaved beams. So we took a multi-mode fiber and then we sent it through a beam quality measurement, which essentially involved this tunable lens and a detector. And my student came down and he said, the light is rotating as it's going through focus. And I said, that can't be right. Please go back upstairs. I have no idea what's going on. And he came back in an hour and said, this is still happening. I think it's real. And then what we realized is that you don't just want to describe the beam quality with a single number, this m squared. You actually want 10 second order moments. And one of the second order moments is looking at how the beam rotates through focus. And it turns out that we had accidentally generated a beam that had optical orbital angular momentum. So what is this? Wow. This essentially means that your beam has spiral or helical wavefronts. The wavefront is the surface of constant phase. And these are often described as Laguerre Gaussian modes. And so they look a little bit like donuts in terms of intensity. But if I look at the phase for an L equals 1 beam, it would have a 2 pi phase wrap. And it also has a phase singularity so that you have a very strong null in the center. And so we got really excited about this. And I have a colleague whom I respect very much, and he showed some really nice results showing that he could propagate beams with OAM through custom fiber. But I didn't have access to the custom fiber. And the running joke is, okay, his fiber costs $100,000. I don't have access to it. So I figured out how to do it with $3. So the goal was to be able to generate this orbital angular momentum in commercially available fiber. So you can add up modes in fiber. So just like many things, if you make your fiber large enough, it doesn't just support your nice, fundamental mode. You can get other electric field solutions out. But if you look at the conventional step index fiber that's used everywhere, when you look at essentially not the fundamental mode, but the next one, you find it's actually 4-fold degenerate. So, and you actually only want to add up 2 of those modes in order to generate OAM. And so if you can mix between all 4, then you're just not going to have something that's stable. And so...
what does 4-fold degenerate mean? And why is that important?
So think about it this way. If you have modes that are very similar in terms of what's referred to as effective refractive index, it's essentially the refractive index they're seeing, then these electric field solutions, any little perturbation can cause the power to slosh between them. And so it can be very hard, for example, to keep them in one of these modes, to keep the power all in one of these modes, if there are another 3 modes that are very, very close in terms of being allowed. And
they
so
have the same group velocity, is that? And
yes.
And so it's really easier for them to just couple into each other.
I mean, what you really need to do to figure out if the modes will couple is you need to do this mode overlap integral. And so it will take into account both the amplitude and the phase. But often people they just plot the modes as a function of effective index. And then look, and if the modes are close in effective index, then generally they will couple easily. And so our solution was to go to polarization maintaining fiber, where you have 2 stress rods. And so this actually breaks the degeneracy. And it turns out now when you go from the fundamental to the next modes, you only have 2. And those happen to be the 2 that we wanted to add up. So we showed that, okay, if we add these up with a phase difference of 90 degrees, then we can generate really good looking OAM beams. We showed this for not only L equals 1, but also L equals 2. And then the big question was what to do next. So we got really interested in this super resolution microscopy that I was telling you about. But if you remember, I said that everything needs to be bend insensitive. And I just told you about adding up 2 modes with a well-controlled phase. So it turns out that is a problem. And along the way, we made a mistake. We were adding up our modes and we weren't getting L equals 1. We were getting like L equals 0.8 consistently. And my student came to my office and said that he wants to publish. And I said, we have to understand what is going on before we publish. And it turns out that we made kind of a rookie mistake. Our mistake was essentially that we were beyond the delay to have proper temporal coherence. And so even though we were well within the coherence length of the source, if we're adding up these modes, we have to add them up with we need to be just really careful about how we launch both sets of modes into the fiber. So once we fixed that, we were able to get the L equals plus or minus 1. But what it showed us was that we had another knob on how we generate this OAM. And so what we ended up doing for instead is we actually do fully incoherent addition, where we just add up the intensities of the modes. And so if the fiber moves around, nobody cares. And by the way...
Because you're beyond this temporal coherence length, you're adding up incoherently, and you're actually taking advantage of that?
Yes. So the STED does not inherently require OAM. What it requires is a donut with a dark null in the middle. And so the phase-sensitive addition is really problematic if you can imagine a fiber moving around. You could imagine that you'll go from having nice OAM to not very nice OAM. And so my point here is that if we add up the modes incoherently, so we're essentially just adding up intensities, not the amplitudes of the electric field, we'll get a donut no matter what happens to that fiber. And that's what we showed.
Because each mode is a donut with a very nice null, and because you're not coherently adding these two different modes, you're not spoiling the null in the middle. Is that the reason?
So I'm going to say something that's going to make you laugh. You probably remember when Professor House got excited about PMD, and he started talking about sausages.
Oh, that was my third thesis topic, actually, PMD.
Yes. So he got all excited, and I've never forgotten him talking about sausages. Okay, so when you think about these higher order modes in the PM fiber, you essentially have like two sausages in vertical direction or two sausages in the horizontal direction that you're adding up. You don't have like two donuts. We're generating our donut from these modes.
Wait, so so you're talking about a second order mode in a PM fiber is a sausage shape, not a donut?
The modes in the PM fiber. So the first one looks like just like a round blob. The second one, you can think of like two lines with some, I don't know, if you were to draw two lines on the board with like a fat marker and say they were two, like an equal sign. Okay. Maybe like one is like an equal sign, the other one you rotate it.
Okay, so that's what they look like. I didn't actually know that.
Yes. So, so when we add those up, we get essentially a donut shape. And then we have shown that we can generate STED with what's referred to as one photon excitation, and also with two photon excitation, so that we can go deeper, and show that we clearly see super resolution in fixed tissue samples.
Wow. That's crazy. So you basically, this is talk about luck again. This is a very serendipitous discovery, it sounds like.
It's really funny, and it's really funny because I didn't believe my grad student. And then also that we fell flat on our face for about temporal coherence, which is something that everybody should know. I just think this concept of the temporal coherence length can be really misleading.
Well, that's great. I mean, aren't a lot of the greatest discoveries accidents?
I think so. So.
Okay. Cool. All right. I think there's like a couple more. You're a busy person.
I am a busy person. So we actually also do a lot of work on integrated photonics.
That was the 7th part of my conversation with Juliet Gopinath. Next time, we'll get into integrated photonics. Juliet also teaches a free online course on active optical devices. Just go to Coursera.org and search on active optical devices, or search on Juliet Gopinath. Subscribe to this podcast, and we'd really appreciate you helping to get the word out. Share this with friends and colleagues that come to mind when you think of network technology and optics. And leave a review on Apple Podcasts. We're also on all the other major podcast platforms. You may see the Cisco Podcast Network come up when you search for Cisco Optics Podcast. That's where we live, and you can find other great podcasts there too. Also, check out the Cisco Optics blogs at blogs.cisco.com and search on hashtag Cisco Optics blog, no spaces and no hyphens. We also have educational videos on YouTube. Just go to youtube.com and search on Cisco Optics. Thank you for listening. This is Pat Chow, Product Manager at Cisco Optics. The next episode is part 8 of my conversation with Juliet Gopinath. Until next time.